Welcome back, everyone. We're going to continue with elliptic curves. We're going to continue with talking about the group law today. So last time we defined the geometric construction of the group law, which is what you see on the screen. How to add 2 points. You trace the line from P to Q that has a third point of intersection R, and then you trace the line from R to O and find the third point of intersection, and that will be P plus Q in general. And that happens the same way, but it looks nicer when you have a Weierstrass model, short or actually a long Weierstrass model. The key here is that there is only one point at infinity, which we call O, and we showed early on in the lectures that every vertical line goes through O. So the curve in green goes to O, and then also every vertical line ends up going through O because, well, that O, the points at infinity would tell you, parameterize the slopes of lines. So every vertical line, that slope is exactly what O parameterizes. So that's why every vertical line goes through O. And the other key property of a Weierstrass model is what we wrote here, that that at O, the tangent line has a triple point of intersection. And that, for example, tells you things like O plus O equals O. It helps you there's a, for example, it also says that when you have that property A here says that P plus Q plus R equals O. So if you have 3 points in a line, the 3 points on your elliptic curve that are collinear, then they add up to 0. And that is actually what we use to construct the group law, that P plus Q plus R is 0. And that's why this is not P plus Q. P plus Q is down here. So that this point up here, this R is actually minus quantity P plus Q. Okay, so knowing what the geometric law looks like, it's not hard to, and we sort of indicated how to do at least B, C, and D to prove that E over K bar, E, is an abelian group. The points on E form an abelian group with this geometric construction. We did not prove, and I'm not justifying here, oops, I wanted the highlighter. I'm not justifying here part E, which is associativity. That is actually quite messy to do, so we're not going to do it here. What we're going to do is wait for a little bit, and we are going to construct again a group law using divisors. And then it's just the group of divisors is a group. It's very easy to see that that's associative, and then show that that addition on divisors on Picard matches the addition on elliptic curves that we just defined geometrically. One other thing we might want to talk about just for a minute is this, that if your elliptic curve is defined over K, then the points over K actually form a subgroup of the points over K bar. So let me just say why that is true. So this is part F. The fact that the points over K are a subgroup of the points over K bar. So why that is that, well, let's just again assume that we're in characteristic away from 2 and 3, but actually the argument I'm going to write, I'm just saving myself some writing. So if you have an elliptic curve, then we just need to know that if I have 2 points defined over K, so, and I have 2 points P and Q, so this is E, so A and B are over K, and P and Q are 2 points defined over K, all I need to know is that R, the third point of intersection in the picture. So when I have this, all I really need to know is that, so here is P, here is Q, and then here is R. All I need to know that R also has coordinates in K, because then at least in the short Weierstrass form, we know that the P plus Q is going to be, if this is whatever, alpha, beta, this point here is going to be alpha minus beta in short Weierstrass form. In long Weierstrass form is actually just like that also, but minus A1 x minus A2 or something. So so it is still a point over K. So what I need to know is, the question is R defined over K also? And well, just take L to be the line through P and Q. P and Q are defined over K, therefore L itself is a line defined over K. Just, you know, you use a formula from pre-calculus of a line through 2 points. Whoops, no, you see, I even forget my pre-calculus. Y equals AX plus B. And those A and B are going to be in K. And then the third point of intersection, I just intersect the two things. So I have y squared equals x cubed plus ax plus b, and I have y equals ax plus b, and that I can just solve by putting ax plus b in the place of y. And this will be x cubed minus ax plus b squared plus ax plus b equals 0. Now this is, what is this? This is a cubic polynomial. It is defined over K. Every constant here is defined over K. And there are 2 roots already that we know that are defined over K. So, and if P is, let's say, C, D, and this is EF, then we know that X equals C and X equals E are roots. Because definitely P and Q are in the intersection of the line and the cubic. Then that tells you that X minus C times X minus E divides my polynomial. And therefore, there is a third root. And since C and E is all over K, the third root is also in K. So this polynomial, let's call it g of x. G of x is monic, so it's going to be x minus c, x minus e times x minus alpha. And alpha has to be also in K, because x minus c and x minus e are in K. Okay, and then is the beta coordinate going to be in K? Because it's given by a quadratic in y. No, but we actually, that point is also in a line. So now using this equation, that tells me that beta is A alpha plus B. It is also in K, and therefore R is defined over K. Okay, and that's all I needed. So if you have points over K, the addition of the points will be over K. And in fact, something that came up before we started the video, somebody asked, in fact, if you have any intermediary field, So if K, we have a field L in between K and K hat and K bar, then so this is a subfield, then EL plus is also a subgroup of E. Okay. In fact, any extension of K is also, so you don't have to go just to K bar. You could go to, so for example, if you're over the rationals, you can go all the way to the complex numbers and get also an elliptic curve over the complex numbers with those equations. And that is also a group, which we will do also in chapter, whatever, chapter 5 or 6 or something. We will talk a little bit about elliptic curves of the complex numbers because it gives a different point of view that is actually quite interesting. All right, so so we have points over K, and that is like group is an abelian group. And now the rest of the course, or the many lectures that are left, is that we want to prove that this group is actually a finitely generated abelian group. But it will take a while to get there. Okay. All that we just said can be made explicit in terms of formulas. I'm not going to do that in full generality. You can find the entire set of formulas in Silverman. In general, I mean, I don't know when was the last time I added 2 points myself by hand. Not recently. Usually I go to magma and then find what's the addition of the 2 points. So but here is how you can come up with formulas. So let me just give you what the formulas look like for addition if you are working with a short Weierstrass equation. So here I'm assuming that the coefficients in the long Weierstrass equation, A1, A2, and A3 vanish, which actually tell you, let me see if I can see that, that the coefficients B2, which is going to come up in the formulas, B4 is 2A4, if I did this correctly. B6 is 4A6, and B8 is minus A4 squared, because all the other ones, A1s through A3 vanish, and the formulas for the B's are easier. So first, you can check this. This is not hard to check that. Well, first of all, the negative of a point, so the additive inverse of a point that we've said already is x comma minus y, because you just have to trace a vertical line and see what the other point of intersection is. Again, you have to be careful that if you have a long Weierstrass equation, the additive inverse is not this. The coordinate y involves the A1 and A3 coefficients. And now what happens if P2 is not minus P1? How do you add a P1 and a P2? Then if P1 is x1, y1, and P2 equals x2, y2, then you can actually just do the formula. So you have to find what is the line between the 2 points, where are the slopes, find the line, find the intersection, and you find what the third point of intersection is, and you can find out exactly what the formula is, which is as follows. Then I'm just going to give you the x coordinate. It turns out it has a nice formula. And again, if you're in long Weierstrass form, there is a few more coefficients that come from the A1 and the A3, I believe. And
what do you mean nice?
What is it?
What do you mean nice?
It's nice. I mean, nice by my standards is that I could remember this, right? it's also nice, it doesn't involve any of the coefficients. It doesn't involve A1 through A6. Isn't that nice? Right? It's the same for any elliptic curve. I mean, of course, the coefficients are sort of like hidden in the y coordinates of the elliptic curve, of the points. But anyway, that's my taste. Okay, so and then if P1 equals P2, then what we are doing is actually probably this is for P, not P1 or P2, but if P1 equals P2, then what we're doing is doubling. I want to know how much is 2 times P. The multiplication by a number, if you are adding 2 points together, we're going to call it as bracket 2. So the multiplication by 2 on an elliptic curve is actually given by x to the 4 minus b4 x squared minus 2b6x minus b8. That's why I told you I was going to need the b coefficients. And it's given by that formula. Okay. So this is typically actually the doubling formula is something that is a little bit more useful than the rest that I've used in the, maybe not recent past, but I've used the doubling formula because sometimes you want to know what are the coordinates of a point such that q times 2 equals p. So you have p and you want to know sort of like what is half of p. So this q that you can double it to get p. And then, for example, if you have a point that is of 2 torsion, a point that is 2 times p is O, you might want to find out what is a point of 4 torsion, and then you can use this doubling formula to figure out where is the x coordinate of it. And knowing the x coordinate, then you can use the equation of the Weierstrass form to find what y is. All right, so I'm not going to prove these formulas. It's just pushing symbols around. Okay. I never did an example. I meant to do an example. So let's do one example here. So take y squared plus y equals x cubed minus 7x plus 6. It turns out this elliptic curve has a name, is somewhat famous. It's called the Gauss, or people call it the Gauss elliptic curve. Actually, not because it appeared in papers of Gauss, but because it was used to prove in the proof of the Gauss class number 1 conjecture. Okay, so the Gauss elliptic curve, also known in LMFDB as 5077A1. I remember that back in the day there was some server of papers that it was like just sort of like known among number theorists that you could go there and there was a lot of papers that one could find there, and the password was 5077. Okay, for this reason. So why this reason? It turns out is the first elliptic curve of rank 3. So it has many points. There are many points defined over Q. In fact, there are many points on this elliptic curve that are integral. And here are, for example, 3 points. And then you can verify, use your formulas to verify things such as P plus Q, it turns out, is 3 minus 4. P plus R is 9/4 minus 15 over 8. And Q plus R is 2 minus 1. So you see that knowing a few points, then you can start doing addition and find more points, and sometimes you even find more integral points on your curve. Okay, so now let me talk about proposition 2.5 in the book, which is the following topic. So we now have that if you have an elliptic curve, you have a group law. So you may ask what happens if you do not have an elliptic curve, if your Weierstrass form is singular, then what happens? It turns out that you can still retrieve a group law even in the case that you have a Weierstrass equation that is singular. So not an elliptic curve, but if it's singular, you still can construct, you still can use the same construction of addition on the curve and still preserve some dignity and still have some group law. So here is the proposition that E be a curve given by a Weierstrass equation, Weierstrass model, with delta being 0. Okay, so for example, if you take y squared equals x cubed minus x squared, that's not an elliptic curve, that is singular. Okay, it's a long Weierstrass model that is singular. So if it is not an elliptic curve, can it still have a group law, please? So so that E has a singular point S. By the way, I didn't prove it, but there is only one singular point. When you have a singularity, the singularities, you can actually sort of like, if you give yourself a model, a Weierstrass model, the point at infinity is smooth. And if there are singularities, they happen, if it's already in short Weierstrass model, they have to happen at one of the points where it intersects the x-axis. And if you have a singularity, you have a double root or a triple root, but you can't have two double roots because the polynomial is cubic in x. So you have one singularity, and that's, we call it S. And let E and S is going to be the non-singular points of E. Okay, so throw away S and look at the other ones. It turns out that, so suppose that E has a node at the singular point. So there is a node, meaning there is a crossing of the graph. Then we saw that a node corresponds with the case of Z4 is not 0. And let y equals alpha 1x plus beta 1 and alpha 2x plus beta 2 be the tangent lines at S. So we have singularity, some crossing like this, and then there's two tangent lines, and those two tangent lines are the ones I'm talking about. So find those. Once you have those, then it turns out that the set of non-singular points is isomorphic to the multiplicative group of K bar. Okay, so ENS meaning ENS is ENS over K bar. Okay, the group of points over K bar that are non-singular. And I can give you the isomorphism. XY goes to y minus alpha 1x minus beta 1, y minus alpha 2x minus beta 2. So this is an isomorphism of abelian groups. In B, the other case is that we have a cusp. So if E has a cusp, then the situation is that we have a cusp, so it looks something like this. So there is a unique tangent line, okay? So if it has a cusp, then let y be alpha x plus beta be the tangent. And as the tangent, it's sort of like, it's not, if you try to find the tangent using calculus, then of course that is not well defined. But from the picture, you can see that there's going to be, if you take the limits, there's going to be one tangent. Okay, so then it turns out that ENS is isomorphic to K bar plus, so the additive structure of K bar, and the isomorphism is given by x minus x, the coordinate of S, divided by y minus alpha x minus beta is an isomorphism of abelian groups. Okay. This, by the way, I'm not going to prove this because I'm actually leaving this as an exercise. The full proof is in the book, but the exercise, so the exercise, which is in the homework, is number 3.5 in the book, is that this can be done over K. With a little bit modification, it's not exactly this. So it can be done over K so that this is either K star or K plus, but you have to modify it a little bit. If, for example, this is the case, if, for example, if the tangent lines are defined over K, then this is the case. One of the two is true. If the tangent lines are not defined over K, then you have to be a little bit more careful. So I'm leaving this as an exercise, so you read yourself the proof of this proposition 2.5, and then work out what happens over K. Okay, that is a good exercise to understand the proof and then understand well enough to actually reproduce it yourself in a slightly more general case. Right, why do I like this result? This result is going to be very useful because we're going to be doing the following ourselves. We're going to go from elliptic curves. So, oh, that's not a good place to write. So we are going to go from elliptic curves, for example, defined over Q. We are going to have an elliptic curve. It's smooth and nice, but I can pick A and B to be integers, and then I'm going to take P to be a prime, and I'm going to reduce modulo P, and then what I'm going to get is a curve that looks the same, feels the same, but now is defined over FP because I've reduced mod P, but this may be singular. Right? The discriminant could have been, for example, of my elliptic curve over Q, the discriminant could have been 7. And if I reduce mod 5, 7 mod 5 is non-zero, and I get an elliptic curve over F7, over F5, say. But if I reduce modulo 7 and my discriminant is 7, then now my discriminant is 0 mod 7, and I get a curve that is singular mod 7. And this proposition tells me what happens to those groups. I used to have a group that was the entire group for the elliptic curve over Q. When I reduce, I get something that is singular, and this salvages the group law so that I still know what happens over F7. There is still some group law, okay? And when we do that and it is singular, this is going to justify the notation that when I reduce modulo P and I get a node in FP, of course, over FP, there is just points. It's not like a smooth curve and you can't graph it, but if the concept is the same algebraically, if there is a node, then I'm going to say that I'm going to get multiplicative reduction when I get a node over FP, and that multiplicative comes exactly from that group, that K bar star. The group law is multiplications, right? This is this group. The same way this is a group under addition, and when I get this, I'm going to say that I have additive reduction. So later on, when those terms appear, they will not catch you by surprise. All right, so I'm going to stop this video here, because then next what I'm going to do is talk about the group law from the Picard point of view. And it's a good place to stop.